Well, hello there. This is Craig Hane, or Dr. Dell, and this is a video for my high school students, and it's entitled The Pythagorean Theorem, Is It Always True? Now let me remind you the Pythagorean Theorem, which you studied in Tier 2, and which we use throughout practical mathematics. If a triangle with a perpendicular angle, meaning a 90-degree angle, or we call that a right angle, has two sides measuring A and B, that's the sides of the right angle, and a hypotenuse C, then we know that A squared plus B squared equals C squared. Now that's the Pythagorean theorem that you learned. And I will tell you, it might be the most well-known theorem in plane geometry. Probably, if there's any one theorem that more people have heard about than any other, it's the Pythagorean theorem. And I'll tell you this, the Pythagorean theorem is the basis of many, many other theorems in geometry. It's an extremely important theorem, goes throughout math. Now, if you go to Euclid's Elements, which was the most published math book of all time, in fact, I think there's more copies of that published than any other book next to the Bible. In book 1, it's next to the last proposition, proposition 47. And the last proposition actually proves the converse, meaning that if you have a triangle where A squared plus B squared equals C squared, then it is a right triangle. And that ends book 1 of Euclid's Elements. And anybody that studied math for centuries, that's what they studied. This is what Abraham Lincoln studied when he was learning math. And right up until the 20th century, this was the most famous book. Now the proof in Euclid's Elements depends on what they call the Windmill Diagram, and it's a very challenging proof to follow. In fact, very few mathematicians or math teachers could sit down and write up that proof with blank pencil and paper. It's hard to follow, it's hard to remember. In fact, I've never seen that proof in any of the modern math textbooks. And the reason is there's much simpler proofs. If you use algebra, then there's many other simpler proofs. Now, I came across a proof some years ago based on similar triangles. In fact, I have a video on it I've prepared, and it's the very best proof I've ever seen. It's only 3 lines long. Can you imagine that? But more important, it really exposes the Pythagorean theorem for what it really, really is. And so that is a video that you can watch sometime. And I thought I had discovered, so I'd never seen it written anywhere, and then sometime later I found out that that was a proof that Einstein learned the most from. So there is a proof now based on similar triangles of the Pythagorean theorem. Very, very good proof. Okay. Now the question is the Pythagorean theorem always true? Well, you would think so. Everybody for centuries, and actually for thousands of years thought, well, the Pythagorean theorem is true. But a hint to the answer to this question is, it depends on the famous parallel postulate in Euclid's Elements. That's a very famous. If you have a straight line and an external point to that line, there's exactly one straight line through that external point parallel to the given line. That's a parallel postulate. Now I'll tell you this, many of our ancestor mathematicians, in fact I'd say most of them, thought that this parallel postulate really ought to be a theorem. It sort of stood out from the other postulates. They thought that they could prove it from the other postulates of Euclidean geometry. And they tried and tried for centuries. Many tried, and they all failed. Some of them thought they had proofs, but they found little some false assumptions in them, and they were bad proofs, and they all failed. And of course, they also thought that the Pythagorean theorem just always had to be true, no matter what. Even though it depended on the parallel postulate, they didn't bother. Well, in the mid-1800s, the mid-19th century, mathematicians discovered that none of this was true. And in fact, the world of mathematics changed forever right in the early 19th century. And the reason is there are plane geometries where this is not the case. And they're called non-Euclidean geometries, as you can imagine. And in these non-Euclidean geometries, not only is the parallel postulate not true, but the Pythagorean theorem is not true. in any of these non-Euclidean geometries. The Pythagorean theorem is not true. Now, plane, plane geometry, really means one that's two-dimensional. So you can go left or right or up or down, but you can only go in two dimensions. It's not three-dimensional. So, for example, a flat blackboard would be an example of a plane, flat Euclidean geometry. Now you might say, well, what's an example of a plane geometry, two-dimensional geometry, that's not flat? Well, the surface of a sphere is an example. We live on the surface, essentially, of a sphere. And it's not flat. We all know that there's a curvature to it. And in fact, that is really the essential difference, is this curvature. The Euclidean plane, like a blackboard, has zero curvature, and the sphere, like the one we live on, has positive curvature. Now, this can all be defined very rigorously mathematically, and I'm not going to get into that, but intuitively it's very clear. You can see where, just think of the blackboard as flat, no curvature. Think of the surface of a ball, like a basketball, is positive curvature, and the same is true of the surface of the earth. Once we realize that the earth is not flat, that it really is a sphere, and that's positive curvature. Now, if you take a saddle, just think of a saddle, that actually has what's called negative curvature, and that would give you another example of a non-Euclidean plane geometry, the surface of a saddle. Now, each one of these geometries is an axiomatic system. If you go back and watch the video on what is math, math consists of axiomatic systems. That's all math is. It's axiomatic systems. Euclid was the first one to come up with an axiomatic system for Euclidean geometry. Now, these non-Euclidean geometries are also axiomatic systems, but the difference is they don't have the parallel postulate. In the positive curvature geometries, they assume that there are no parallel lines. There are no parallel lines, so you can't have a line at an external point with a parallel line through it. And in the negative curvature geometries, they assume that given an external point to a straight line, there's an infinite number of parallel lines. So those are the differences. Now, the consequence of the parallel postulate in Euclidean geometry is that the sum of the angles of any triangle are exactly 180 degrees. And I prove that, demonstrate that in Tier 2, very early on. It's very easy to demonstrate if you've got the parallel postulate. But in a positive curvature geometry, like we live on in the sphere, the sum of the angles of a triangle is greater than 180 degrees. And by the way, that non-Euclidean geometry we call Riemannian geometry, after the great mathematician Riemann. Now, in Euclidean geometry, one of the most important concepts is similar triangles. You can have two triangles that are different sizes, but of course they can still have the very same equal angles, because the sum of the angles is always 180 degrees. So if two triangles are different sizes but have the same equal corresponding angles, they're called similar. But they're not necessarily congruent. Congruent means they have to be the same size. So if you're actually proving theorems in geometry, angle, angle, angle does not imply congruence. It only implies similarity. And furthermore, in Euclidean geometry, you have theorems about the ratios of the sides and the angles of similar triangles. We did all this in Tier 2. This is extremely important in practical math. Euclidean geometry, by the way, is still the math that we use in most of our practical math when we build things and all the things we do. Even on the surface of the earth, if you're not over too big a part of the surface, you can still think of it as a plane. And so Euclidean geometry is still what we use in practical math. And the facts of the matter are there's these wonderful proofs about similar triangles and their ratios. Well, in Riemannian geometry, if two triangles are similar, then they're actually congruent. So if you're proving theorems in Riemannian geometry, AAA works to prove two triangles are congruent. You can't have similar triangles of different sizes in Riemannian geometry, and that's a big deal. That makes Riemannian geometry tremendously different than Euclidean geometry. So if you're going to study geometry on the world we live on, the surface of the earth, it's a very different deal. And so much of the math that we have learned and that is true in Euclidean geometry is not true in Riemannian geometry. Now, in particular, the Pythagorean Theorem is not true in Riemannian geometry. In Riemannian geometry, if you have a right triangle, which you can have, of course, a squared plus b squared will be strictly greater than c squared, never equal. And that's a big deal. When you're navigating long distances on the Earth, that has profound implications. Euclidean geometry will give you very, very incorrect answers as you're navigating on the surface of the Earth. I'll also tell you this, if the radius of a sphere increases, then its curvature decreases. And what that means is there's really, in a sense, an infinite number of different non-Euclidean planes, Riemannian planes. But there's only one Euclidean plane. There's only one plane with zero curvature. Lots of different planes with different size curvatures. Now, this is all proven rigorously by theoretical mathematicians. Ever since the 1800s, they've worked on this as in the axiomatic systems and proven all this. So what you could say is the Pythagorean theorem is almost never true, meaning there's an infinite number of different planes where it's not true, and there's only one plane where it is true. And when that happens, mathematicians like to say it's almost never true. Now, there's going to be another video I'm going to do for you, and the title of the video is going to be 1 mile south, 1 mile east, 1 mile north. That's the title. Think of that. Start at some point, go a mile due south, a mile due east, a mile due north. And the question is, where are you going to end up? And I'm going to explore that on the video. And you got to remember, I'm talking about now on the surface of the Earth, where we live, the world we live on, as I say. So, 1 mile south, 1 mile east, 1 mile north. Here's a question. If you follow those instructions, where are you going to end up? Now, I'm going to give you a hint. If you said 1 mile due east to where you started, that's almost never true. It is sometimes. Where is it true? If you want to understand navigating on the Earth, where would that be true? And where is it not true? As a matter of fact, is it possible that you could end up right where you started? Since I asked a question, you think, well, maybe it could be. And then the question will say, okay, if that can happen, if it could happen at all, how many places could it happen? Maybe it can't happen at all. That'd be 0 places. Certainly if the Earth was flat, the answer would be never. If the Earth was flat, the answer to this question would be you'd end up exactly 1 mile due east of where you started. But the Earth's not flat. It's round. It's Riemannian geometry. So the answer might be 0, but it could be 1. Maybe there's a place where that could happen. Is it possible it could be more than 1 places? Is it even possible it could be an infinite number of places? That's a question I'm going to address and answer in that video. But you might be thinking about it. This is high school math, and what you want to start doing in high school is thinking about things and exploring and asking questions. As a matter of fact, mathematicians have many, many more questions they don't know answers to than questions they do know answers to. What you do is, as I said in the video, what is math? You set up an axiomatic system. That's something we invent. We come up with the undefined terms and the axioms. Then we start asking ourselves, what could be proved now? And that's discovery. Discovering theorems that can be proven. And it's a never-ending job. Mathematicians every year discover more new theorems they didn't know before. Every year. And they constantly are inventing new axiomatic systems and exploring them and seeing what could be true in them. And then, of course, the scientists want to take these different axiomatic systems and create math models so they can understand the world we live in better. And that's been going on now for really since Euclid and the Greeks, and even before them, Babylonians and other people started doing it. But it's really picked up steam in the 20th century, big time. It all kind of started in the 19th century. When we discovered non-Euclidean geometries in the early 1800s, the early 19th century, that really was a change for math. All of a sudden we realized, oh my golly, there can be lots of different axiomatic systems. Oh my golly, different ones have different applications. As a matter of fact, Newton used Euclidean geometry for Newtonian physics. Everything he did was Euclidean geometry. And there were things he couldn't quite explain that didn't fit properly. Well then, Einstein came along and he used Riemannian geometry. Einstein could not have done relativity theory with Euclidean geometry. It used a form of Riemannian geometry, more sophisticated than what I've talked about here, but a form of non-Euclidean geometry. And that was relativity theory. Wouldn't be relativity theory without that. So what we've been doing now, really starting in the early 1800s, we've been developing more and more axiomatic systems and studying them, creating math models with them to try to get better scientific models, better to understand the world. And believe me, we're nowhere near the end of that process. A lot of people think that, well, we've come a long way. Compared to where we were, we've come a long way. But we're nowhere near the end of the process. And you as a high school student need to start being aware of this is what the world is like. This is what we're going through. And as time goes on, we're going to have more and more math, more and more axiomatic systems, more and more math models. We're going to understand the world better, and so on. And in fact, as I mentioned in some of my other videos, there's a wonderful new scientific theory by William Tiller that goes way beyond the classical current scientific theories that I happen to think is the right way to go. I think he's the modern Galileo. Well, anyway, that's getting off the subject now. But you see, I get excited about this because you need to get excited about it. That your life depends on excitement. It depends on exploration, making new discoveries, learning more things, making mistakes, lots of mistakes. You go down a lot of dead-end paths, but you learn a lot as you go. And so this is going to be, hopefully this has opened up your ideas and your mind to new concepts, and it'll hopefully excite you to continue on learning. So this is Dr. Dale. I'll see you on another video. Have a wonderful life.